Um, so hey everyone, so let's get started. So welcome back. So let's start with the brain teaser we talked about. So last question on Thursday. So hopefully you've had enough time, to think about this. So does anyone, now that they've thought about it a bit more, think they have the right solution? No. Oh, okay. Okay, it was a good brain teaser, huh? So okay, would you like me to explain, or would you like to think about it a bit more? Yeah. Okay. Yep. It's an isolated event. It's that's the information you're given. So so we're going to use conditional probability, and we're going to condition on the event that one of the two coins was found, and it was one of the coins was found heads up on a Tuesday, right? So it could have been the first coin that was heads up on Tuesday, or it could have been the second coin that was heads up on a Tuesday, right? But either one of those two was is the condition. Was another comment? Yeah, you in the middle there. So do you have an explanation behind it? You can make, there's a guess up there, 1/3. Well, if we looked at question 2, right? So if you remember question 2, if I found at least one coin was heads up, the probability that the other coin was found heads up was 1/3. Yeah, so we actually went over this before. So let's see, the space, the sample space of finding two coins is either they're both tails up, right? That's what I shaded in pink. One's the smaller one was tails up, the bigger one was heads up. That's this one here. The bigger one was heads up, smaller one tails up, that's here, and they're both heads up here, right? And we know that one was found heads up. So it's one of these three spaces, right? So we're conditioning on being in this region here, right? And then we say, what's the probability the other coin was heads up? And there's only one instance, so 1 out of 3. Yeah. We don't know which coin was heads up. It could have been both. It could have just been one. All right. So we condition. If you write down the sample space, we have restricted the sample space. That's what the conditional probability is doing. I'm restricting to the event that at least one was heads up. And that means only 3 possible outcomes now, and they're each one was equally likely. Okay? And so now only one of them had the other one heads up as well. All right, so is question 2 kind of clear to everyone? Because if this isn't clear, then my explanation of the part 3 is not going to be clear either. It's like this, but it's more complicated. All right, let's try and go through question 3. Right, I'm going to need a new slide here. So let me. All right, so we have 2 coins. We have so the big coin and also the small coin. We're going to take a cross product of these spaces. All right, the big coin has 2 possible it has heads and it has tails, but it also has the day of the week that it was found, Monday, Tuesday, Wednesday, Thursday, Friday, Saturday, and so Sunday. So the sample space of just the Bitcoin, because I've specified the day of the week, it's got those 14 squares up there, right? You can see those little squares on the paper or the fake paper. All right, and so similarly for the small coin, I'm going to have two of outcomes for heads and tails, and I'm going to have the Monday, Tuesday, Wednesday, Thursday, Friday, Saturday, and Sunday, and I'm going to have 14 things in the so the sample space for the small coin. And so that means that if I know I'm going to find, so, you know, a possible instance of this, one possible instance would be to find the big coin heads up on a Saturday and the small coin tails up on, so a Wednesday, right? So the sample space here is size 14, 14 and 14 here. So the total sample space, if here, the size of it is going to be 14 squared. Okay, so there are 14 squared different possible outcomes. Okay, but we are, so conditioning, so now, so we're going to have, so the so Tuesday event, this is, so one coin was heads up on, so Tuesday, right? So we're going to condition on this event. So I'm no longer going to have the 14 squared, you know, size sample space. I'm going to have a restricted sample space. All right. So how big is the restricted sample space? I'm going to say I'm going to have this. So the sample space heads on Tuesday. How big is this sample space going to be? So how many ways can I find one coin heads up on a Tuesday? Yeah, there are kind of two possible ways. It can be the big coin, it can be the small coin, but I need to consider everything else for all the other coins, right? So there are two ways of thinking about this. One is that the you know, big was heads up on a Tuesday, and then times 14, right? Because there are 14 ways that the small coin could have been. The other way is 14 ways that the big coin could have been, and that the small was the heads on heads occurring on the Tuesday, right? So that says there are 28 different ways that this can occur. So does this make sense that there are 28 different ways I can get at least one coin heads on a Tuesday? Yeah. Good. It's very good. It's not 28. It's not, because one of these 14s was with, this could include the small coin being heads up on a Tuesday, right? So I've counted that instance twice. Okay, so I need to have both the union of both of these sample spaces minus the intersection of them. All right, so it's going to be 14 plus 14 minus the intersection, which is going to be, so 27. There are 27 possible outcomes given that at least one of the coins was heads up on a Tuesday. Okay? There are 27 ways I could do. Each of them are equally likely because I don't know what day of the week it was. I don't know what if the coin was heads up or heads tail, but I know at least one of them was heads up on a Tuesday. It's possible both were heads up on a Tuesday. Okay? Okay, so now the question was, what's the probability that the other coin was heads? It didn't need to be heads up on a Tuesday, but was the possibility the other coin was heads? All right. Okay, so let's look at this. There are I just need to look at that the second coin was heads, and this is the sample space. Well, then there are two ways to analyze this. One is that the big coin was heads on a Tuesday, and that the small coin was heads on a Monday, Tuesday, Wednesday, up through Sunday, right? So I could pair these together. There are 7 possible combinations here, right? If the big coin was heads up on a Tuesday, this second coin could also be heads up on a Monday, Tuesday, Wednesday, Thursday, Friday, Saturday, or Sunday. And similar with the small coin, heads up on Tuesday. So this set is of size 7, and then small coin, and then the heads on Monday, Tuesday, up through up through Sunday. This is also of size 7, but I've double counted Tuesday here and Tuesday here. That's when they're both. So those are the same event. So I'm going to do plus, this was equals 7. So I'm going to get, but I have to subtract the intersection. So I get 7 plus 7 minus 1, which is going to be 13. So there are 13 different ways the second coin can be heads up. Okay, and those are all equally likely. So the total, right, is going to be 13 divided by 27. 13 divided by 27. This restricted sample space has size 27, and there are 13 outcomes. This is about 0.48. So pretty close to 50-50, right? I give more information, but it's kind of creating a lot of the sample space, but there's a small intersection between both sides of so kind of occurring. All right. Okay. Yeah. So there's, yeah, the intersection is the event. The big occurred heads up on Tuesday, and the small occurred so heads up on Tuesday. That occurs in both this top row and the bottom row. But if the big occurred heads up on Tuesday and the small occurred tails up on Tuesday, well, then that tails up on Tuesday is not this event. That's different. But it has to be heads up on Tuesday, right? So there's only one intersection, right? There are 2 events out of the 28 which are identical to each other. So I need to subtract that. Yeah. Yeah, so in these brain teasers, you kind of need to kind of make that implicit. I didn't say, well, it could have occurred on any day of the week. It happened to occur on Tuesday, and all the days are kind of random. Historically, it's close enough to picking. If you pick like what day of the week was I born on, I actually don't remember. It was, as far as I remember, probably it was equally likely Monday through Sunday, right? Yeah, I was so too young to remember, I guess. I could probably figure this out. But that given I told you it was a Tuesday, there are roughly equal number of days in the week that I could have possibly found these coins. So that kind of implicit in the problem. Yeah. I told you it's a fair coin. I said it was a fair coin. I could have said equally, it could have occurred on a random day of the week, but it's kind of implicit. Yeah. 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 So all I'm claiming is that at least one of them was heads up on a Tuesday, right? Now that on a Tuesday gave more information. If I just told you one of them was heads up, it's only a 1/3 probability the other is heads up, right? That's what this analysis was about, right? But if I give you more information, one of them was heads up and it was a Tuesday, then it changes the probability from 1/3 to 48%, almost 50%. That's why it's a brain teaser. Teasers your brain a little bit. Yeah. Hopefully it's clear. If it's unclear, you can ask and we'll try and clarify. Yeah. Yeah. This is more of a thing to stimulate your intellectual curiosity that's related to the subject of the class. And as question like this will probably be harder than what you'll get on the quiz. Yeah, or the homeworks, right? So, but this is meant to kind of show you kind of why it's, I'm hoping most material I'm lecturing about and that you're being evaluated on is fairly easy for you, and you, as I lecture, and you're all going to do well, but that there are harder problems underneath that can keep you, so can keep you thinking. All right, one last comment, then we'll kind of move on a little bit. It does not imply that. The other one, the event I'm interested in, the other one's heads up. Could have been heads up on a Thursday. That counted. Just as heads up. So think of, if I look at the sample space on the top, all of the parts up here are heads up. All those are heads up on the yellow. They could occur different days of the week, but they're heads up. As long as I matched it with one of them occurring heads up on a Tuesday, it doesn't matter what the other is, as long as it's heads up, it satisfies the event I would like to know the probability. So okay, so let's move on a little bit. Just a little thing to keep you kind of so interested a little bit. So a little administrative stuff for the course. The first homework is due at the end of the day today. I saw about half of you have uploaded already, which is good. And most of the uploads are correct. Your upload should have 6 pages. The assignment had 6 pages. Your upload should have 6 pages, include the cover page. I spot checked about a third of them, and 1 out of a third forgot to upload the cover page. If you have kind of extra work you want to show, put that at the end of the document so it won't mess up the alignment of stuff. And write on the sheet and scan that or take a picture of it and turn it in. Again, of the 50 I spot checked, 1 of them did not do that even after my reminder with an announcement on Canvas. Okay, so we'll try and be somewhat lenient this first time, but afterwards we'll be less lenient after this first assignment. Okay, and so you have time to re-upload stuff. You still have time. It's just, just a reminder on this. So it seems like most stuff is going well on that. Reminder, office hours, there are still, yeah, so we've had most office hours. Are you going to have another one or? Yeah, okay, and I'll be around after class as well to help answer last minute questions, but these are due tonight. There's you can turn it in late and get a late penalty. Hopefully on the first assignment, you're not trying to use that too much yet. But so I recommend you'll start getting a late penalty after Gradescope, so marks it late. Okay, due technically at 11:50 tonight. But there might be a little slack in the dates, in the timing given on Gradescope. All right, so make sure you turn that in. We had one update on the office hours in the future. That was kind of cool. You could see it a little bit. So Megna's office hour, she had some scheduling issue, and they'll be shifting next week to Monday from 1:30 to 3:30. if this presents a major problem for your schedule because of this last minute change, let me know and I'll also see if I can address it. But I assume it's still roughly the same day. That might even be a better time for for some of you. Hopefully that's okay. Okay. Yeah, I just wanted to also review a little bit about some stuff on the syllabus while it's kind of relevant for you right now. The late policy is 10% each day it's late. As soon as it's marked late, you've lost 10% on the assignment. And if you're over 24 hours late, you've lost another 10%. If it's more than 48 hours late, you won't be able to get a grade on the assignment, okay? If something very difficult in your life has happened, as will happen with the class this size, unfortunately, throughout the semester, please let me know. We'll see about if something can be done. But I want to emphasize, don't think about cheating over that, right? If there's an issue where you're like, I don't know what I'm going to do, I don't know, come and talk to me instead of thinking about cheating. That's the wrong answer on this. The homeworks are designed for you to learn. You can kind of work somewhat together on these, but on the final, you won't be able to do that. So the semester is geared towards you learning the material. And so by the end, you'll be asked to do the final by yourself in here on paper, and you should be ready for that. The homework quizzes are designed for that. Okay, so in collaboration policy, you can kind of sit and talk about them together, but write them up by yourself. Don't don't like write long answers on the board and just copy them all together. We will probably spot it. You probably have heard about ChatGPT and this stuff, which can maybe do some of your homework questions for you, maybe less so in this course than other courses. I don't recommend using those. You're not going to learn if you're using those in this class. One of the things about AI is that it might help you answer questions, but it also helps us instructors detect if people are cheating on questions. If you notice, there's software out there that can detect if something was written by ChatGPT with pretty decent accuracy. I don't think you want to be thinking, are you going to go up against that AI? So kind of don't be cheating, and don't turn something in that might make me think you're going to be cheating. Neither of us wants to have that sort of conversation. Yeah, and so, consequences can be pretty severe. Like it's not that often that we catch cheaters, but when we do, the consequences are pretty drastic, including if you get 2 strikes, you can no longer take courses within the School of Computing. It's pretty, you're not going to complete the major if you can't take any more courses here. Okay, so yeah, so keep that in mind as you do this. Again, they're designed for you to learn. The worst thing is definitely cheating, not quite knowing how to do it or asking for help. There are lots of help hours leading up to this point. All right. Want to mention one other thing. The quizzes, I think, have been going pretty well. Yes, there's some silly mistakes on question, but in general, you guys are doing about as well or better than I was, expecting on the quizzes. So that's great. Quiz 2 will also be on Canvas on Thursday. This one will not just be multiple choice. You'll be asked to write a little bit something in a box. So, if you've taken them on the phone and you're not proficient at typing on the phone, you might want to consider doing it on a computer. If you think you're fine on the phone, it's not going to be too complicated. Okay, it's meant to be simple, to be done quickly, but just a warning ahead of that, because the first couple were just multiple choice. We're sometimes going to ask you to fill in blanks. The grading will then be done. The TAs are going to have to check the grading, so it'll take a little bit for the final grades to happen. So just be patient on that sort of stuff. All right. Okay. Good. So let's get into the lecture. Okay, great. So independence. All right. So independence is a pretty important property within. So within probability. So we're going to consider. We have 2. So events. A and B, and we say that A is independent of B when the probability of A given B is equal to the probability of A. Okay. All right, so this is our core definition of independence. What in English, kind of English words without using mathematical terms of kind of explaining what this, so what this like equation means. Right? Yeah, in front?
Means that knowing that A occurred does not affect how likely B is to occur.
It turns out that is correct, which we'll see, but you've kind of switched A and B here a little bit to read this off directly. So we'll see that's not wrong what you said, but what I would interpret this as the probability that A has occurred does not depend on whether B occurred or not, right? So this says this is the conditional probability of A. If you remember, the conditional probability of A given B is the probability of A intersection B divided by the probability of B, right? So the conditional probability of A given B, so if we know something about B, that's the probability of A given that knowledge. Well, that means this is the same as the probability of A occurring. It did not affect that outcome. Yeah. Can you say it a little louder? That the probability of B is 1. You're thinking because you're dividing through by B here. It does not. Yeah. So if you know that probability B occurred, right, then given that knowledge, then probability B, we've restricted to that sample space. So there's some sense in which on this side of the equation, probability B is kind of 1 because we know it occurred, but that's not true on this side. Okay, and so I wouldn't, that's not the right way to think about it, even though there's sometimes you can think that's true, but that's not the right way to kind of internalize what's going on here. That's kind of the right thing to do, you know, when we have this case, the probability that at least one of them is heads, well, that is 1 because we're restricted to the sample space, right? But in general, that's not the right way to think about it. All right. So okay. So yeah. So if this is not true, right? Then so if probability of A, so given that B is true, is not equal to the probability of A, right? So if this is not true, then we say that A is dependent on B. Okay, so then it depends on B. The outcome of B affects the outcome of A, right? So a lot of the problems we talked about with like choosing, like if we choose balls out of some urns, right? And what the first ball we picked, well, that affects what the second ball we're going to pick, right? If we have these black and white cards and we pick out, we look at one side of one of the cards, that affects the probability of what the back side of the card's going to be, right? So on your homework question, right? Okay, so most events are going to be so dependent only if this equation is exactly true. Are they going to be independent? Okay. All right. Okay. The next thing I'm going to do is kind of this formula is kind of a key formula that's that's here. But I next want to do a little bit of algebra and show you that there are other, it's equivalent to some other formulas, and oftentimes those are easier to work with. Okay. Okay, so we're going to start with this basic formula of independence. Probability of A given B is equal to the probability of B. Okay, and so this is going to be equivalent if I expand out the definition of, so conditional probability, right? So remember the definition of the conditional probability of A given B is equal to the probability of B divided by, of A and B divided by the probability of B. Then this should also be equal to, hold on, I wrote a mistake up there. It should be the probability of A. Okay, this should also be equal to the probability of A. Those are equivalent statements. I've just expanded out the definition of, so conditional independence. Okay. So what I can do, so that's just by definition, right? So this isn't really changed much, but I can now multiply through by the probability of B. So now I can say that the probability of A intersection B is equal to the probability of A times the probability of B. Okay, so this is another useful kind of definition of independence. Okay, so I have the one at the top, which I started with. Okay, but I can also write that the probability that A and B are both true is equal to the probability of A is true times the probability that so B is true. All right, this form of it is kind of like one of the central premises that most of like machine learning is based on, that you have a bunch of observations which are data, and you look at the probability of observing that data point under a model, and you assume that the data points are independent. So I just look at the probability of each data point that I observe and I multiply all these together. Right. So this is kind of a really central kind of form of this property of independence. Okay. Okay, but there's from here I can actually expand. I can also make another step. I can also go the probability of A given B, and I can divide through by the probability of A. Right, so I could do this. This is also equivalent, right? Divide through by A on both sides, and that means I can also simplify this. This is the probability of B given A is equal to the probability of B. Okay, so this is the third form that is very common. Okay, so this is saying the probability A and B are independent, or A is independent of B if the probability of B is unaffected by whether A is true or not. Right? So this is the English explanation that we got before, right? A is independent of B if the probability of B is not affected by A. Kind of a direct way of reading off this expression. That's equivalent. So A and B independence, the order A to B or B to A is equivalent to each other, right? So this is a symmetric operation or symmetric property between A and B. Okay. So if we know A is independent of B, then B is independent of A. Okay. And so it's just algebra here based on the definition of the conditional probability. All right. So these are the three main forms, and they're all equivalent to each other. All right. Okay. So let's go through an example. Okay. Okay. So we're gonna, let's say I'm gonna have a fair die and I'm going to throw it so 2 times. Okay, and I'm going to say that so A, the event A is going to be that the sum of the values is so 5. Okay, the sum of the values is 5, and so B is going to be the event that at least one throw is a 2. Okay, so I'm going to throw it 2 times. The first event is a separate thing from the second event, right? So I can have snake eyes where I roll 1 1, right? Okay, so if I write out the sample space of A, right? So the event A is the sum of the values is 5. That's going to be 1 4. The first one is 1. The second one is 4. It's an ordered pair, right? 2 3, 3 2, and 4 1. Right? Those are the only outcomes where the sum of the values is 5, right? So there are values 1 through 6, so I can't row 0, right? If I row 6, it's too much, right? So these are the only outcomes where the sum of the values is 5. Okay, and the B, right? So the event V is at least one roll is 2, right? So it's 2 1 2 1, and I'll just write them without the parentheses to simplify a little bit. 2 3, 2 4, 2 5, 2 6, right? And then I can also have 1 2. That's different from 2 1. 2 2 I already have, right? So if I do 2 2, I want to actually cross this out. This is the same as over here. So 3 2, 4 2, 5 2, and 6 2. Okay. So sometimes if you have a lot of things to write out, you might skip the ordered pair and just write 2 numbers next to each other if that's quick, right? Okay, so this is the sample space for B. Are these independent of each other? Okay, so how should we attack this? What should we do to try and see if these are going to be independent from each other? Yep. Oh, okay. So you want to start by calculating the probability of A intersection B, right? So maybe start by looking, and that would involve calculating A intersection B here, right? And good. So the intersection looks like it's probably small, so this is a good thing to start with, right? So the probability of A intersection B, is there a typo or a comment? Yeah, so this event 2 2, that's saying I threw the first die as 2, and this said and the second die is 2. This says the first die is 2 and the second die is 2. Those are the same thing, right? So right, I can think of the whole sample space here as a 6 by 6 matrix, right? Right, there's 1 2 3 4 5 6, 1 2 3 4 5 6, right? And one the columns are the first die, the first row, the rows are the so are like the second row, and this element is 2, 2. That's the same element, right? There are 36 possible. This will be useful. There are 36 possible outcomes, right? So the sample space is going to be 6 times 6, 36. 36 outcomes. One of them is 2, 2. But you see there are 35 other outcomes there, right? Okay. Good. Right. So that's why we don't count this second one as a distinct event. Those are the same thing. Okay. So the intersection now, let's figure out what's the size or what's in the intersection. The only ones that look like they're going to be in the intersection are 2, 3 and 3, 2, right? They have to have a 2 in them. And so the probability that both of them occur, both events, is 2 out of 36. Okay. All right. Okay. Good. That's a good start. How do we use this to check independence? That's what we need to check one of those. So equations, we had 3 choices. Which equation do you want to use? Do you want to? One of them, this is a good one. This one has probability of A intersection B, right? So that's in this equation. So why don't we try check this one? Then we need probability of A and probability of B. Okay? And these seem like things we could probably calculate here. Probability of A, right? Well, that's just the size of A divided by 36, right? So that's 4 divided by 36. There are only 4 different possible outcomes in A. And the probability of B, okay, how many outcomes are there in B? I'm going to say there are going to be 11. Is that right? Yep. There are 6 outcomes with 2 as the first die, and 6 outcomes as 2 as the second roll, and 1 intersection, which I subtract. So I wrote out 12 things, but I subtracted one of them. That's going to be 11. 11 divided by 36. Okay, so now we need to check if the big question is 2 divided by 36 equals to 4 divided by 36 times 11 by 36. This is 44. 44 divided, well, usually good to try and cancel here. Maybe cancel before we multiply. 1/9, 11, 36. It's still not easy, but it's 11 over, what's 36 times 9? That's 324. Is that right? Yeah. Okay, good. Is that 2 out of 36? This is a nice 1 out of 18. No, those, I think I've simplified them both pretty well. So this is not true, right? So they're not independent. Okay, so this is how you would do this sort of calculation. So these would be not independent, because P of A intersection B, the probability is not equal to the probability of A times the probability of B. Okay? Seems, you just have to write out the sample space, count, figure out the probability of the 2 events, and then kind of plug them into one of these equations and check. Okay, so yeah, I'll go through maybe towards the end of the lecture. I'll go through some kind of maybe some complicated, some brain teaser like questions about independence that show that you really want to check this, because sometimes you can't really just reason about it. Sometimes you can kind of reason about it. All right, how about I try another example? And maybe this one you can kind of reason about, and then we'll check the mathematics. Okay, so I'm going to have, so 2 urns, okay, urn 1 and urn 2. Okay, and the two urns have, the first one has 4 black balls. 1, 2, 3, 4, and it's got 3, so let's say red balls here. 3 red balls, okay. The second one is going to have 2 black balls and 2 red balls. Okay. So I'm gonna select one of the urns at random, and then I'm going to select a ball. Okay, so I'm gonna select one urn. So with equal probability, and then one ball. Okay, so the question is if so we'll call this U1 and this will be U2. Okay, is U1 independent of red? That I so that I select a red ball. Okay, so this is choose urn 1, and this is select a red ball. All right, so are these events independent of each other? Does the choice of urn affect the probability of selecting? Does it affect the probability of selecting a red ball? Yep. So yeah, right. If I select the first urn, then I'm less than 50-50 chance going to select a red ball. But if I select the second urn, then it's a 50-50 chance, right? That means probability is 0.5 of selecting a red ball in the second urn, and probability is 3/7 out of selecting a red ball from the first urn, right? So that so matters. These are not independent. You can kind of reason about that, right? We can work this out quickly with one of these tree diagrams too, right? So we can say this is U1, this is U2, right? This is 1/2 probability, 1/2, right? And then I have 2 options. I have red and I have black. This is 3/7, this is 4/7, and on the bottom it's 1/2 and 1/2 of red and black, right? So the conditional probability here, what this element right here is, this is the probability of red given urn 1, right? And so the question is this equal to the, I could calculate this, is this equal to the probability that I select a ball that's red? Well, I can calculate that here. This is 1/2 times 3/7. But I could also select a red ball down below here, where I get this 1/2 plus times 1/2, and I need to add these up. Okay, so the total probability of getting something red, and this is the rule of total probability, which we'll cover maybe this lecture, maybe next lecture, is going to be then 1/2 times 3/7 plus 1/2 times, so times 1/2. Okay, and that's going to be equal to, so I gave myself a tricky one, huh? Okay, so 3, and not a lot of room to work with down here. All right, so that's 3/14 plus 1/4. Okay, and that's going to be equal to 6/28 plus 7/28. This is going to be 16 over, not 16, 13 over 28. Right? That seems about right. Slightly less than half, which makes sense. But the probability for was 3/7. So 3/7, this is not equal to probability of red, which was equal to 13 out of 28. Okay, so these are also not independent. So the answer was not independent. Okay. All right, okay. All right, well, so is all this, okay, do you want one more example on this level, or do you want something maybe a little bit more kind of so thought-provoking? It's pretty clear how to approach this. Oh, so what would happen if I changed the number of red balls in urn 2? What if I changed it and I added 2 more black balls? Actually, well, what did I say? 8 black balls. So I have now 8 black balls, and I put 6 red balls. Okay, is the probability I select urn 1 independent of the probability I select a red ball now after this change? Yeah, now it's going to be independent because it's going to be 3/7 probability. It's the same ratio of red to black balls in both of the urns, either 3/4 or 6/8. 6/8 simplifies to 3/4. Right, so if I add those balls and I make it even in the urns, even though it's not the same number of balls, it's the same ratio, then I still have independence here. All right, okay, it seems I need to do something more thought-provoking. You guys are following along, hopefully finding this straightforward and easy. Let me ask a little trickier question. And maybe we'll have you discuss amongst yourself. Let's toss a coin 3 times to find 2 events. A is at most 1 t. Okay. At most 1 tails occurs of the 3 flips, right? So those are the 3 events where at most 1 tail occurs. And B is the event that both heads and tails occur. So I cannot, it's the complement, right? That C is the complement of all heads or all tails. Are these independent? All right, so how about if you guys break into discuss with your neighbors and work this out, and we'll come back. Oh, and gosh, and yeah, and maybe you can do a breakout room. So if you think you have the answer, confer with your neighbor. Sure. So, okay. So, so how many people think they have the answer? Just raise your hand if you think you have the answer. Okay. We're still kind of working on this a little bit. How many people were checking, their phone or Facebook and stuff? No? Okay, good. Yeah, at least you're still thinking about it, or you just didn't want to raise your hand? Okay. All right. If I can get you to raise your hand at some point, that's something positive. Okay. All right. So who believes A and B are independent of each other? All right. And who thinks they're not independent of each other? Okay. All right. So some controversy. All right. So for those who think they're independent, does someone want to say why they think they're independent? What's their reasoning? How about here?
So
Okay, great. So you did this where you said the probability of A was 4 out of 8, right? Probability of B is going to be then 6 out of 8. Okay, and the probability of the intersection A and B. So that would occur. This one, and this one, right? Those are the 3. So that's 3 out of 8. Okay, now we need to check the product. So we're going to say check the product of A times the probability of A times probability of B. This is equal to 4 out of 8 times 6 out of 8. It should be equal, let's see, this is going to be 1/2 times 3/4, which is 3/8, which is a match here. All right, is this, so you did it? All right. Okay, good. Does anyone have a discrepancy with this or a different insight of how they approached it? Yeah. Oh, A is the sample space, at most 1 tail. Oh, 8 as the sample space. 8 as the sample space. Yeah. So the sample space is it's these repeated sample space, right? So the one flip has a head or a tail, right? And so the size of this is 2. Okay. And so then when you say, well, I do a repeated trial, each trial can see either of those outcomes. So the 3 flips is 10 is tails or heads to the power 3. 2 to the power 3 is 8, right? So when you have a repeated sample space, you look at one instance and then you take it to the power of the number of repetitions. So if you have two coins that are tail, it's 2 to that flip. If you have a die that you roll multiple times, it's 6 6 to some power, right? 36 was 6 squared before. Okay, great. Okay, good. This one was a little bit good to work out. All right, here's something else useful. So one way that independence is useful or not is when things are not independent. Something you want not to be independent is the relationship between some sort of like a medical test and like an outcome. Okay, so if you want to know if you have COVID, you take one of those COVID tests, and it might not be perfect, but you want that the outcome of the COVID test to be not independent of whether or not you have COVID. If they're independent, it means that the probability you have COVID is independent of the reading of the COVID test, right? Okay, so you want those not to be independent. So here's an example, a generic example where you have two cases: you're sick or you're well, you have COVID or you don't have COVID, and you want to have a test that says, positive meaning you test positive for COVID, negative, and maybe means that you did not perform the test properly, right? If you didn't, I don't know if you ever have to spit in those little tubes or something, you didn't, do the right amount of spit or something. Okay, so if you have an example like this, you want to know, does the test, can you use the test to help predict whether you had COVID or you have flu or something else? Okay, and with a test where this example of a probability table. Okay, so this cell here, this cell is the probability that you are sick, and the test is positive, right? So that happens 0.005% of the time. Okay. Okay, and similarly, this cell is that the probability that you are well, and the result is inconclusive. It's a maybe. Okay. So if you add up all of these, it should be equal to 1. Okay. Okay. So is this test helpful to predict the disease? Yeah, questions? Oh, so no is your answer. Yeah. So do you have Oh, okay, great. That's a great question. You need to know the probability of being sick in the first place. Well, you can read it off one of these probability tables, right? The probability of you being sick is actually going to be the sum of these 3 rows. All right. If you're sick, you're either going to get a positive, maybe, or negative, right? And this is a rule we'll talk about. So I think in the next lecture, the rule of total probability, right? And so I can calculate the total probability of being sick here. Yep. Sure. If you want to add to the answer, yeah.
Yeah, I would say that yes.
Okay, so if you get positive tests, you have a 5% chance of being sick. Okay. And what's the chance that you're sick to start with?
That would be
The chance you're sick to start with is going to be the sum of all those green things. I think this is also 0.5%. So the chance that the probability that you're sick giving you're positive looks like it's 0.05 divided by 0.01, right? In fact, I've pre-calculated. These are the probabilities of getting positive, maybe, or negative out of the people who've taken this test, right? So 0.01, 25% got a maybe, and 65% got positive. And the probability of being sick and well is the sum of those rows, right? So this is equal to the probability of being sick. This is the probability of equals to well. You know, this is the probability of getting a negative on the test here, right? All right, so there's someone said this is not helpful. Someone says this is helpful. So what do you all think? Yeah. Yeah, okay. If you are sick, yeah, so this could still be the case. So there are some helpful tests where this is the case. So there's some kind of screening for like some, for like some rare events, right? So let's say being sick is pretty rare, right? You're only 5% chance being sick. So most of the people who take the tests are actually not sick. All right, so it's not surprising that yeah, so so that might not be so surprising. All right, do you guys want to discuss amongst yourselves and try and figure this out, or comments? No, it's point one, right? So I should have that. If I look at this row down at the bottom, this should add up to 1. Yes, good. This should be 0.1. Okay, yeah, good. So thank you. All right. Yeah, so how would we check if this was helpful? So if these are going to be independent, they're not going to be helpful, right? So how would we check if an event that I tested? Oh yeah, we actually did. Yeah, no, we didn't do this yet. All right, so the probability of being, let's say the probability of being sick, given the probability that I test so positive, is this equal to the probability of being sick? Right, so that seems like a useful thing to try and check, right? If this is equal, then they're independent of each other. Okay, so the probability of being sick, we had that as this is equal to 0.1, 10% of the chance you're sick after this correction here. Okay, so let's say the probability of being sick given testing positive is equal to the probability of sick intersection of positive divided by the probability of positive, right? And so we know this numerator, let's use different color, this numerator is exactly up here, right? That's exactly reading off this table, 0.005. And the probability of testing positive, we can actually read that off the table too. Of testing positive is, well, down there, 0.01, 0.01, 0.1. Okay, good, after the correction. Okay, and I made another mistake. That was also a mistake. The probability of being sick was 0.05. We also have this here. Okay, good. And so we want to check if 0.005 divided by 0.1 is equal to 0.05, and that is the case. This is 0.005 divided by 0.1. This is equal to 0.05. So these are going to be independent. Okay. That still doesn't mean that the test itself, just checking this one square, does not mean that the test itself can't be useful. The test still could be useful. Okay. But it just means that the testing positive does not affect the probability you're sick. It could be testing negative affects the probability that you're that you're not sick. Okay. And there are 3 columns here, so we can't kind of just totally reason about this. There are these things we'll see later in the semester saying these like random variables, and that is the probability of sick, well, positive, being the outcome of the test could be sick or well, and the outcome of the test could be positive, maybe, or negative, and the state of the patient could be sick or well. Those are kind of random variables we'll see about. And so you have to check all possible events to see if it's not useful or not. But I think in this case, if you check all of the possible cells in the table, you want to basically take 2 items. Okay, you want to check this cell, and you check, is it the product of these 2 cells of the things at the bottom, the marginal distributions written in the margins of the tables, right? So to check if they're independent, you need to check every one of these cells. If it's the product, this would be the probability of sick and maybe. Is that equal to the probability of sick, which we have in the blue, times the probability of maybe, right? And so that's the case here. 0.0125 is 0.25 times 0.05. So you have to check every single cell to see. Otherwise, if any of the cells don't match, it might be somewhat useful. Maybe not very useful, but might be slightly useful. Okay. In this case, everything matches. So these are going to be independent. It's not helpful to predict the disease. Yeah. Yeah. Sorry. Thanks. Sometimes I get off the edge of the page. This is probably a sick and maybe. Is that equal to the probability of sick times the probability of maybe? Okay. So if those are equal for all kind of cells in the middle of the table, right, that the product of the marginals is equal to that, then it's then you're going to get that it's independent. Yeah. So they were pretty effective. They were, it wasn't, so like if you went to like a facility with trained people to take the tests, I think it's probably like we'll talk about how to measure the effectiveness kind of when the statistics part of the course. But, I think if you were sick, then something like 99% of the time they tested it. They reported you were sick if a trained professional did it. And maybe there was a false positive when they reported you were sick when you weren't, somewhere less than 5%. I think it was in that range. If you did it at home, some people weren't very careful, and there were some other issues. But those tests were quite effective. And it varied. The first tests that came out were less effective than now the tests available are very effective. Okay, well, let me ask one more kind of brain teaser to think about, and then I won't work on this one. This one you can think about, how does this work by yourself? Okay, so I've got an urn with 4 balls in it. Okay, the balls have labels on them, and so binary. Okay, and these are the 4 possible labels. You know, you could imagine other binary labels, but there are only 4 balls, and these are the 4 balls. Okay, 1 1 0, 1 0 1, 0 1 1, 0 0 0. Event AK for K 1 2 or 3 is the event that you got a 1 in the second place, right? So the probability of A2, or I'll just say the event A2 is equal to just 1 1 0, 0 1 1. Those are the only 2 of those 4 balls that had a 1 in the second position. Okay, is A1 independent of A2? Okay. Well, actually, how about A2 and A3 and A1 and A3? And maybe check this, and then how about a intersection of A1 and A2 independent of A3? All right, question. I'm only drawing so I'm not replacing, I'm only drawing 1 ball. So I'm drawing 1 ball, and then I'm checking, is event A2 true? Right? And so this question is event A1 and A2 true? Is that independent of A3 being true? All right, so let's just to get you all started, is A1 independent of A2? Yeah, this is both. This is going to be these should be independent of each other. Okay, A1 should be independent of A2. Okay, okay, and it's actually symmetric. The states for this sets A1, A2, and A3 are all kind of so symmetric of each other. None of them include this one, right? And they all include 2 of the other ones. So A1, A2 are independent, A2 and A3 are independent, A1 and A3 are independent. We'll see that, but is A1 intersection A2 independent of A3? So this is actually an instance of an important kind of concept within computer science that shows up in things like the theory of hashing, which shows it's useful in how you kind of compress really big data sets on top of each other. And you need these things that are these hash tables, these random kind of selections of hashes, which are multi-way independent of each other. And what you might see here is pairwise independence, but you might not get kind of something like 3-way independence. Right? So you get different types of independence between different events. Okay, I'll let you think about this, and maybe we'll revisit this at the start of the next lecture once you've had a chance to ponder it a little bit.
I have 2 questions.
Great. Let me pause.